Here is a short video of my project. As you can see, the 8-bit microprocessor is very modular in the sense that it can be assembled separately. So at the top left, you have your A register, your adder subtractor, B register, and output. And starting from the left side, it'll be your program counter, memory access register, random access memory, and instruction register. In order for everyone to get a better understanding of the control unit, I decided to be able to control these outputs manually. That way we can walk along with the program. Down here is your output, so that will be displaying the result from the output register to here in binary. And in order for us to get a better idea of the instruction set that was created, at the very bottom I have the decoded logic to take the most significant bits from the instruction register and output them onto these LEDs to display which instruction is being executed. Here's a short program for the microprocessor. I made sure to include one of the newer instructions that I added, which would be the jump instruction. So the way this works is each address will, using the memory access register, each address will store the set of 8 bits. The first 4 bits indicate the instruction to be executed. So if you remember the instruction set, 0000 is LDA, 0001 is add, and so on. The last 4 bits represent the address in memory in which this data is located. So once it goes through the memory access register once everything is loaded in the instruction register, these last 4 bits will go back into the memory access register to access these contents. To show that the jump instruction works, I just placed the last 2 instructions further down the program. Down here, I just wrote the last 3 execution cycle signals. That way I can remember to walk through each step individually. As each control signal is being active, the program, not the program counter, but the system clock will pulse. That way the information is stored at each execution cycle. So this is the system clock that I was referring to earlier. Right now it's pulsing at around once per second. I can use this potentiometer here to speed up that clock, but for the purpose of walking through the program, I'm going to switch modes. That way we can control the clock with the use of a push button. Alright. Okay, so to save time, the microprocessor was already programmed with these 2 dips, which is the program that I mentioned a little earlier. So we're going to first go through the fetch cycle, which the first state is the address state. So I'm going to bring out the program counter onto the bus. Since the program counter is already 0, it's going to display that. Then we're going to activate the memory input for the memory access register, the address input rather, and that'll be loaded onto the memory access register. And then, as you can see, it's 0, so currently the data is pointing to location 9, and we're gonna pulse that. Then we're gonna bring these signals low, and for the second stage in the fetch cycle, we are going to put the data from RAM into the instruction register. So starting off, we're going to bring the output of the register to high to display the information on the data bus. Then we're going to activate the input to the instruction register, and on the next clock pulse, that information is going to be loaded into the instruction register. Now that we went through our program counter, we will go through the execution cycle, 1 cycle at a time. So since the first instruction is LDA, since they're all zeros, you can see down here, after the contents of the instruction register are outputted to this decoder determines which instruction is going to be executed. So right now, the LED indicating LDA is lit up. So now, we're going to send this address back to memory. So we're going to make the output high for the instruction register. It's hard to see with the wiring. So that outputs the data from the instruction register back to the data bus, and then we're going to use this as an input for the memory access register. And then on the clock pulse, it'll be loaded, and it loads the data that is located at that specific memory location. Okay, so we're going to be loading this data onto the A register right here. So first, we're going to make all these signals low. Then we're going to jump to the next step in the execution cycle, which is to input the data from RAM, send the data from RAM to the A register. So we're going to make R0 high to transmit that data. Then we're going to allow for input into the A register. And then on the next clock pulse, the information is sent from the data bus into the A register. So pretty much, you're just going to go through each instruction and follow the program in order to get your correct output. Okay, so I got a bit of a head start on the jump instruction. The program counter is set to 3, which is where the jump instruction is. The signal CO and MI have been made high, and it's loaded into the memory access register on the next clock pulse. Did it not load? Okay. Alright, got it. So the jump instruction should be loaded onto the data bus. So make these signals. So RAM in is high, instruction in is high. The data bus is extremely buggy. There. So now we should be getting our jump LED. There we go. So that's the jump LED. So now we want to go to address 6. So it'll be instruction register out to memory register in, clock pulse, and the upper 3 bits are high, which indicate this is the out instruction. So we're going to put these signals low, route out high, instruction high. Then on the next clock pulse, it'll be sent to the instruction register, make it low again, and this indicates that the output, that's the encoded output signal. Then we're going to take the A register, the output of the A register onto the bus, and send it to the output register on the clock pulse. So that's the actual output. There's an LED hidden behind this wire. So the output is 6C. That's the answer to the arithmetic. So 4A plus 3, 4 minus 1, 2 equals 6C, and that's the result.